in the same type of atoms, carbon to carbon double bond in alkenes. But over here, we have the double bond between carbon and oxygen. And because of this, it gives it that dipole action in that the sharing electron, the covalent electrons are not equally shared. So to say, we have the oxygen partially, the electrons spending longer time with the oxygen, so it's partially negative, more electron rich than the carbon of the carbonyl. This we will see very soon, but let me quickly say that the carbonyl carbon is bonded to 3 other atoms, as you can see here, utilizing the 3sp2 hybridization, which are separated approximately by about 120 degrees. The unaffected p orbital of that carbon of the carbonyl overlaps with the oxygen. That is what is responsible for the pi bond that makes the double bond. It's a little distorted, like I said, because of the more electronegativity of the oxygen atom in the carbonyl bonding. So the carbon of that carbonyl and oxygen with 2 other atoms, which I'm representing here as RR, are bonded to that carbonyl bond. You will see that it's established that all these are in form of a flat molecule, and that gives it the ability to easily participate in reactions, or rather an attacking material can come from the top or from the bottom, since it's a flat molecule. Now coming back straight, on the carbon in the carbonyl is slightly electron deficient, hence we say that any system that is coming there should be electron rich, that is, should be a nucleophile, in other words, a base. So these can easily form bonds with the carbonyl carbon, and as the nucleophile approach the carbonyl bond, it bonds to the electron deficient carbon. And that is why reactions peculiar to these carbonyl compounds is referred to as nucleophilic addition reaction, because a nucleophile attacks the electron deficient carbon of the carbonyl, and that's where the reaction commences from. Actually, the flat shape is trigonal, like I said earlier, so the attack would be from below or bottom of the plane of symmetry of the molecule. Now, these carbonyl compounds are found in other groups apart from aldehydes and ketones, though we refer to them as the main carbonyl compounds. But we have other sets of homologous series of compounds that contain carbonyls, such as your esters or alkanoids, such as the carboxylic acid we're coming to next week, God helping us. Then the anhydrides, the acyls, the amides, all these possess carbonyl bonding in them. And for aldehydes and ketones, that polarity affects a lot their reactions, as well as some physical properties, such as their boiling point. The polarity of the carbonyl group in aldehydes and ketone is responsible for observed higher boiling point of this compound, especially when you compare it with hydrocarbons that have equivalent or similar molecular weights in them. The only peculiar thing you should take note of here, unlike in alcohols, is that it doesn't undergo intermolecular hydrogen bondings. So that is why it has slightly lower boiling points when you compare them to their analog or similar molecular weight alcohols and carboxylic acids that have some hydrogen bonding in them. So this set of alcohols and carboxylic acid have slightly higher boiling points compared to these carbonyls. Now, these carbonyls, we group them into 2. We have the alkanals, that is aldehydes, and the alkanones, which are the ketones. Now we want to do a comparison, or so to say, be familiar with the 2 groups. When you have the alkanals, they have the carbonyl carbon always being terminal. That is, it's always taking number 1 in terms of the numbering when you are numbering the molecule. So it's always terminal. Whereas the carbonyl of the ketone, the carbon of the carbonyl, is never terminal. It's usually bonded to either alkyl or aryl group on the two sides. So, and let me quickly say here that when you compare the two, aldehydes are generally more reactive, more susceptible to that nucleophilic addition reaction which the carbonyls are noted to undergo. In other words, aldehydes are better reducing agents when you compare them in terms of reactivity to ketones. We will see more of this later. Now, as to some examples and trying to consider some of their uses and applications or importance. Now, that is for aldehyde this time. The simplest member, methanol, happens to be industrially a reactant when you are manufacturing polymers in the plastic industry, carpets, fabrics, insulators, and some other domestic materials. So this is put into use in such aspect. Then your very common formalin contain majorly methanol, where it is utilized as active germicide or as a disinfectant or in preservation of any biological specimen. Then the next member in the aldehyde is the ethanol. Ethanol is utilized much in synthesizing or producing ethanoic acid, also known as glacial acetic acid. We also touch this when we come to carboxylic acid. This aromatic aldehyde, benzaldehyde, is a naturally occurring pleasant smelling compound, and we have a lot of its derivatives in foods, flavors, and it's utilized in fragrances, even in perfumes. We have a number of derivatives of this benzaldehyde. One of it is, benzaldehyde is naturally occurring too in almond. Then one of its derivative is this vanillin, which I know you all love ice cream. That is the flavor in ice creams. 3-methoxy-4-hydroxybenzaldehyde, that's the structure there. Then we have another aromatic aldehyde, which is our 3-phenyl-2-propanol in cinnamon, is referred to as cinnamaldehyde. Now for the ketones, some examples and their uses. The simplest ketone is propanol, commonly referred to as acetone, though it's trivial but highly acceptable. They are good organic solvents. They are utilized too in rubber cements and paint industries. They are also utilized as nail polish removers. And when you are sweating, maybe during fasting especially, the odor that comes out of such being is also propanol. Also in uncontrolled diabetes, you have propanol, being characteristic of such people. And then high protein diets, when large amounts of fats are metabolized for energy, you have propanol being produced. Another notable ketone is this butadiene. You can see it over here. That's the structure. It's one of the unappealing odors of the armpits when you sweat. Another notable ketone also is this carbonyl, and that's it here. It's a flavor compound found naturally occurring in the oil of spearmint. Menthone is another, also utilized in flavoring. This is wonderful. Muscone is a very important ingredient of perfumes, especially these musk perfumes. We have this simple cyclohexanone, which is an intermediate in manufacturing of other chemicals used in a particular stage of production of nylon. So we now go straight to how we obtain, synthesize, or prepare these two carbonyls we are targeting, the aldehydes and the ketones. I want us to recall a trend we are used to right from even our secondary school, and that is the redox trend, When oxidation is going one direction, reduction is going the other direction. But let's consider it in terms of oxidation now, since we are considering the alkanals and the ketones. You will recall that in the alcohols, which has earlier been treated with you, we have three types of them: primary, secondary, and tertiary alcohol. You know how to differentiate between these three, I believe. Now, when you oxidize a primary alcohol, it will first produce an aldehyde, and further oxidation will result, or finally to give you your carboxylic acid or alkanoic acid when it's aliphatic. The secondary alcohol oxidizes to ketone and stops there, while the tertiary alcohol oxidizes and does not even participate in oxidation at all. And we will see some good reasons for this very, very soon. Recall that the carbon carrying the functional group OH has 2 extra hydrogen in primary alcohol bonded to that carbon. Whereas for secondary alcohol, recall that that carbon carrying the OH functional group is also bonded to just 1 hydrogen, while there is the carbon carrying the hydroxyl on the functional group for tertiary alcohol does not bond at all to any hydrogen. So that's the major difference between these alcohols. Now I have this drawing before you to show the trend of oxidation. In that, all on the left are hydrocarbons. Depending on the structure of your hydrocarbon, whether there are some branchings and whatever. So when we have the first one there, oxidizing, you have it producing a primary alcohol, which I've just given the information about now. Further oxidation will give you the aldehyde, and finally you come to oxidize it to the carboxylic acid. You will find out there's a trend here, which I want you to, the same thing goes for the next hydrocarbon, which has just, this one have the carbon we are oxidizing is bonded to 3 others, whereas this is bonded to 2 others that result to finally give the ketone. And when you have the hydrocarbon with just 1 hydrogen, it oxidizes to your tertiary alcohol, which does not undergo oxidation. And in this perspective, you will notice that in that oxidation of the primary, secondary alcohol charts, which we've just considered, that every time 1 hydrogen is removed from the carbon that is bonded to the functional group OH. So, but in tertiary alcohol, the carbon bearing the hydroxyl functional group is not bonded to any hydrogen. That is why it will not oxidize further. You can see the carbon of this, the carbon linked to the functional group OH does not have any hydrogen, so it cannot oxidize further. Whereas this one has 1 hydrogen, so that is why it's oxidizing further. This one, you can see even 2 hydrogens. That's why its oxidation continues like that. So that is a major chemistry, or using chemistry to see why oxidation is taking place in one and it is not, is prevented in another. Now, that trend too is what we refer to as oxidation. And every time when you are going the direction, or want to determine whether the direction is oxidation, try and look at the CH bonds on the reactants. Is it decreasing and the number of CO bonds increasing? When such happens, you have oxidation. The number of CH bond in this top one where I have my cursor, 3. And then after oxidation, it's reduced to 2. But there is a CO bond. So 1 bond to oxygen. So this movement from here to here is oxidation. So that's how to know whether oxidation is occurring or not. And if you move from this stage to this stage, you will notice that the number of CH bond has decreased from 2 here. You now have 1 CH bond. And then the number of CO bond is now 2. So in this direction, that is oxidation. So vis-a-vis the other ones too, that is the trend over there. So we have seen that. Let me quickly say that there are some common reagents you are used to in your secondary school, that when you see these reagents, you can, reacting on your material, you can say, oh, this reagent is going to oxidize the alcohol, and so on and so forth. Such reagents include these chromium compounds. One of them is this chromic acid, H2CrO4, and it is actually formed from chromium trioxide, CrO3. And another reagent is this sodium dichromate, which easily foster oxidation, is an oxidizing agent, so to say. Then the normal trend, more or less a repetition, sorry, but I'm doing it so that you people can take it up once and for all. The secondary alcohol will oxidize and stop at ketones, while tertiary alcohol will not undergo oxidation. And you have these ones as examples for the for what we are talking about. Butan 2 all happens to be a secondary alcohol. So on reacting it with that chromium compound, specifically here the chromium trioxide in acid medium, you have it producing the ketone, the corresponding ketone, which is butanol. So you can easily determine what the product is. This is also a secondary alcohol, a cyclic alcohol, cyclohexanol. With sodium dichromate, you have it producing your ketone, the cyclic ketone, cyclohexanol. You can do this as assignment, though I have the answers on the next slide, show those structures and also the name of compounds that will be formed from each of these alcohols. Let me quickly say 1 to 4. I pray we have extra time for tutorials later, but 3-hexanol, if you draw the structure, you can prove easily that that is a secondary alcohol, while the next is a tertiary alcohol. So straight off, we know that oxidation of this will not be possible. This happens to be a secondary alcohol, but 2 of it in a single molecules. So finally, you are going to result to have a diol. So to say, I'm also giving you the answer from that, which is formed from that diol, according to the name. This one too, but this is primarily the COH functional groups are primary. And though there are 2 of them, and by the time it oxidizes, first to the aldehyde derivative, and finally it gives a dioic acid, 1,4-butane dioic acid. So just to show it further, what we have been saying, propanol happens to be a primary alcohol. Oxidation, yes, aldehydes are formed from oxidation of primary alcohols. We know that one. But if our primary alcohol is not reflux inside that oxidizing agent, I'm generalizing now using O, any of them, you can collect your aldehyde easily. That's if you don't involve heating, refluxing. But many times you have, in the presence of more oxidizing reagent, you have what is formed, that propanol, further oxidizing to propanoic acid. And that's why I'm putting it in bullets. I've darkened it to show that it can further oxidize. So now in obtaining the synthesis of these carbonyls, I want us to consider these reagents, this oxidizing agent. Actually, we have dealt with the first one. I've labeled them as A to G, A to F specifically, and I want you to take cognizance of the reagents, maybe some chemistry of it, and some limitations or advantages or disadvantages of each one. Like, well, quickly, let's go to the next slide. Just take note, A to F is what I'm going to treat this morning. We have treated this earlier. Anytime you have these chromium compounds, they pass through, for a primary alcohol, we oxidize first to the aldehyde and finally the butanoic acid. So generally, primary alcohol is, when it's not reflux, produces your aldehyde, which you can collect. But on refluxing, in the presence of more of the chromate material, you have it oxidizing to the carboxylic acid. This shows that aldehydes are good reducing agents. We've earlier said that aldehydes are more reactive. They are better reducing agents than ketones. And the second part is utilizing, like I said, is utilizing pyridinium chlorochromates. I'm going to shorten it, or rather we normally shorten as PCC, pyridinium chlorochromates, as our oxidizing agent in the presence of dichloromethane. This has a special advantage in that the oxidation, you can stop the oxidation in aldehyde. You can see it's not aqueous system that we're using it. The next one, I'm just going to go through when I come to the slide of each one, is known as the SWAN oxidation of the alcohols, where we're making use of this dimethyl sulfoxide, CH3, two of it in SO2, in SO, then oxalyl chloride, which is a dimer of COCl, and then triethylamine. That's the reagent that gives the SWAN oxidation of our alcohols. Now, this is much better in that we are not making use of the dangerous chromium-based reagent, which we have earlier touched in A and B. It's quite more human-friendly in this number C. And also, the added advantage which B has is that you can stop the oxidation at production of aldehyde, if that is our focus and our interest. Then the D is preparing our aldehyde through cleavage of a 1,2-diol, utilizing periodic acid. We will see details of or examples utilizing that reagent HiO4. That's our periodic acid. The E1 is oxidative cleavage. When we say cleavage, is cutting actually of alkenes, and that is ozonolysis, which I know you are used to. We also touched a little bit of it when we were treating nomenclature. Okay, sorry, under ethers2, I'm not too sure. Well, I know we've treated ozonolysis, which can be used in characterizing our alkanes. So, but the workup condition we determine can have a long way to show what we are aiming at. You can work it up under reducing agent or oxidizing agent. Whenever you see reagents like zinc or dimethyl sulfide, that is a reducing workup. That's the second step of the reaction. While in hydrogen peroxide, as the workup condition, then that will be oxidizing agent. The F1, we will be preparing these carbonyls from dihalides. Let's quickly start checking them up. From the B, where I showed you earlier before I went to just talk generally about all of them. And that is utilizing the PCC, which has the special advantage of stopping the oxidation. You can, last week I told you that anything I write in red, please take cognizance of that. So utilizing this PCC as oxidizing agent affords us to stop the oxidation of primary alcohol to obtain the aldehyde. So that is, it doesn't further oxidize to give the carboxylic acid, because that's our target. So the oxidation of primary alcohol, such as the butanol, you have downstairs there, 1, 2, 3, 4, that's butanol, in the presence of PCC as our oxidizing agent and dichloromethane, will give us the corresponding aldehyde as our end product. Now the SWAN oxidation, like I said, utilizes these three reagents: dimethyl sulfoxide, oxalyl chloride, and the triethylamine. In SWAN oxidation, it's a very good method, better off than the earlier, meaning that it's not chromium-based, because the chromium-based reagents are somehow toxic to human beings. So the use of chromium-based reagents are toxic, hence this method of oxidation of alcohols is a development or a better method. And another good thing it does too, like number B, is that the reaction is not carried out in aqueous solution. So you have the oxidation of any primary alcohol, stopping at obtaining the aldehyde. That is no further oxidation of the aldehyde, as in the earlier one, PCC oxidation. Then, but still good enough, utilization of the SWAN oxidation on secondary alcohols gets your ketone prepared. So these are vivid examples of what we are talking about. Here you have your propanol, which is our primary alcohol there, undergoing the Swan oxidation with those three reagents and giving us our propanol, which is our aldehyde. So, and even when you have a secondary alcohol, you have the corresponding ketone. Over here now, you have butan-2-ol, the secondary alcohol, and you have it producing your butanol. So we have it there. Now, the third aspect is oxidative cleavage of the 1,2-diol, utilizing the periodic acid, HiO4. Look at this example here beneath, where you have a 2-methyl 2,3-butane-diol undergoing that oxidative cleavage. Yes, this is a 1,2 because they are neighboring the oxygen, carbon-oxygen functional groups. Two of it are neighboring carbon. Now, over here, let me go straight into what you will recall that to get your 1,2-diols, you can do that easily by hydroxylation of your alkenes, where the alkene is oxidized to a 1,2-diol utilizing simple reagents like your potassium permanganate in cold basic solution. You can also make use of osmium tetroxide, that's OSO4, to form the vicinal diols, the glycols or the diols we're talking about. The 1,2-diols, which is now formed, can oxidize to ketone or aldehyde, depending, that is by utilizing that periodic acid, depending on the structure of your diol. When, and it's not far-fetched, reactions occur, okay, the chemistry that utilizes, or the chemistry behind this reaction is that in that same reagent, this periodic acid, reacting with the diol, the 1,2-diol, you have the iodine there is in +7 oxidation state. You can see it where my cursor is here with 7 different bonds on it. So this easily attacks the diol, the 1,2-diol at that position to form that cyclic intermediate, and which further breaks on hydrolysis. Then check on the carbon carrying the ols, the 2 ols. If the carbon carrying the ol is also bonded to an extra hydrogen, like in this place where I have my hydrogen, my cursor, there is an hydrogen bond on this carbon. That is what is responsible for the aldehyde after the break, the cleavage of that cyclic structure. It results to the aldehyde parts of that diol. If the carbon having the OH functional group is not bonded to another hydrogen, like where my cursor is here, then after the cleavage, you have it being a ketone moiety, a ketone material. So for this particular compound, 2-methyl 2,3-butane-diol, you have these are parts responsible for the ketone, which is a propanone, and then these parts of the cleaved molecule responsible for your phenol, which is our aldehyde part. So if the carbon is bonded, that is, if the carbon linked to the OH is bonded to R and an H, like here, then the product will be an aldehyde, as it is in here. But if the carbon that is bonded to the OH group is also bonded to 2 alkyl groups, no hydrogen on it, then the product will be a ketone. What I've said earlier is what I've displayed therein. So it's just bringing it clear over there. Now, another example, utilizing that same periodic acid, this is cyclic diol, 1,2-diol, which is a 1-methyl 1,2-cyclohexadiol diol. Now, the cleavage will be here. Notice that this carbon here is not linked to any hydrogen, and that is what is responsible for the ketone end of that cyclic structure that has cleaved. Whereas this carbon bonding to this OH has one hydrogen that makes it tetravalent, though I didn't show it here, but there is a hydrogen bonded to it. After the cleavage with the pyridic acid, it is what is responsible for the aldehyde functional group on the other side. So, well, this final product, if you will name it iupacly, is heptanal with 6 on. That is on carbon number 6, you have the on therein. So, the E is preparing our carbonyls through oxidative cleavage of our alkene. Generally, alkene can be oxidized to carbonyl compounds by reacting with ozone, O3, or any potassium permanganate, another oxidizing agent. Now, this alkene at low temperature with ozone in particular, we see that the double bond breaks, and that carbon and carbons that are doubly bonded to each other, it breaks there to give the carbonyls where you have the double bond. Now the doubly bonded, bonded to each other are now doubly bonded now to oxygen. It was a single carbon double bond. Now we can see each of the carbon now double bonding to oxygen, double bonding to oxygen. So that is what is ozonolysis. And there is a workup as a second step or stage of this reaction. That workup, can you all say workup where you are? Good. The workup can be by oxidizing agent, or it could be by reducing agent. And I want you to take cognizance of that. When I put X, I'm saying that it's not, I'm not going to put it into, that is, it's important, it's good, it's a fact. How ozonolysis occurs, formation of the molozonide, and finally the ozonide, which is cyclic, and then the breaking to cleaving to carbonyls. But it's not. So where we are going is that when the ozone, the oxygen, O3, sorry, attacks the double bond, we have this ozonide being formed. That's the cyclic structure. In the presence of, now let's consider it one by one. The next slide, this one is having a reducing agent. It's either zinc in H2O, or you have CH3 sulfide, dimethyl sulfide therein. This, whenever you see it, exam or whatever textbook, it's depicting reduction condition. That is, the material is a reducing condition, is in reducing condition. And depending on the structure, you will have your ketone or aldehyde. Now, where you have hydrogen peroxide, it's the workup condition, that is after the formation of the first step is ozone attacking the double bond to form this ozonide. The workup, if it is oxidizing condition, you now have the aldehyde that is formed further oxidizing to the carboxylic acid. In fact, that's the major difference. For the reducing condition, this reagents, that is the dimethyl sulfide, if that is what you are using, or zinc, the final product maintains, depending on the structure, as ketones or aldehydes, or both of them. So product will be ketone when the sp2 carbon of alkene is bonded to 2 carbon-containing substituent. Now, product will be an aldehyde if at least one of the substituent bonded to the sp2 carbon is a hydrogen. I've explained that earlier. So these reducing agents prevents our aldehyde from further oxidizing to carboxylic acid. That is this condition. So cleaving ozonide now in this reducing agent of zinc or dimethyl sulfide is what is referred to in the workup condition as under reducing condition. Please take note. For under reducing condition, the aldehyde form doesn't further oxidize. If aldehyde is formed at all, it doesn't further oxidize to the carboxylic acid. Whereas if the workup condition is an oxidizing condition, you have the products, the ozonide cleavage in presence of oxidizing agent like hydrogen peroxide. If you have that, the product will be ketones and carboxylic acids or both. Reason being that carboxylic acids are formed instead of aldehydes. And that's because the aldehyde that gets first formed will immediately oxidize further to the carboxylic acid in the presence of this H2O2 oxidizing condition. So cleavage in the presence of hydrogen peroxide is called working up the ozonide under oxidizing condition. So please take note of that as good chemistry students. Those are good chemistry you are learning from here. I have these examples which I want you to work with. Yeah, in the class, I wanted us to work with some, and which I'll surely do quickly. But just sit down on your own self and try to work out what will be, try to predict what will be the ozonolytic products in each of these conditions or these reactions. Like you have over here, of course, all of them contain carbon-to-carbon double bond. So just take cognizance of where the carbon-to-carbon double bond is and perform ozonolysis on them and see the condition. The first one there, utilizing the second stage workup condition will be what? That's an oxidizing condition. If any aldehyde is formed from here, it will further oxidize to carboxylic acid. The second one, II, is under what? It's under a reducing condition. That's the dimethyl sulfide. Don't forget, even this next one is the same too. It's a reducing condition. The same thing for IV, even though the same reagents, but that is for IV and V. But this is under oxidizing, the V is under oxidizing condition. So one carbon fragment obtained from the reaction of a terminal alkene with ozone will be oxidized to methanol. That is it. If the ozonide is worked up under reducing conditions, then you will have that methanol finally obtained as methanoic acid. But that is if it is under oxidizing reagents condition. So as the IV and the V, we're going to show this one. And you have your answers, which I've placed there. You can always mark up yourself. I've given the solution to the questions I'm giving. That's why I call it a classwork. I'm happy, but please, I have very close to 300 students in class, but that is still not too good. I'm supposed to have like 1,000 of you, I think so. Though I don't know whether some of you are sharing with one another over there, but make sure you don't miss lectures, please. It's very, very important. Like I said earlier, just immediately you come in, make sure you give your information, even the link you are using, you can give your details there. Now, still on preparation, the last one there talks about preparing your carbonyl from dihalides. Now, take cognizance of the structure of your dihalides. When there are two halogen atoms bonded to the same carbon at the end, that is, and a very good example is this 1,1-dichloroethane over here. You see, in the presence of this mild alkali, barium hydroxide, it hydrolyzes first to the 1,1-diol, which loses a molecule of water to give the aldehyde. So this is a very good example of how to prepare. Now, if the two halogens are on a carbon in the middle, that one was terminal on 1,1 on the very first carbon, and that's why you're having aldehyde. But if the dihalide bonding is in the middle of the chain, that is not terminal, then you have a ketone being formed. Look at this example. We have a 2,2-dichloropropane under this mild alkali, barium hydroxide, hydrolyzing, you have the diol, which finally results to give you propanone, which is a ketone in that case. So predict product of reaction of this with each of this. So you can always work that up. It's very, and that is the answer over there. For the first one, we produce a butanone, and for the next one, it's an aldehyde because it is a terminal dihalide. You have the dihalide on carbon number 1. Now we check on the reactions of these carbonyl compounds, and recall what I said earlier about the flat system, the carbonyl, and trigonal shape, and possibility of attack. Okay, the polarity too of the carbonyl, such that a nucleophile can easily come up to attack the electron deficient carbon, and that is why the reaction that carbonyls will undergo is referred to as nucleophilic addition reactions, where you have the nucleophile bonding on the carbon of the carbonyl. And we can see every other thing there, given that the nucleophile here happens to be a Z attacking the carbon of the carbonyl. You can see it, the adducts there. And then finally on her hydrolysis, instead of the carbonyl, you now have the hydroxyl functional group being introduced therein. So the main feature of the nucleophilic attack on the carbonyl group is the attacking group Z bonding to the carbon atom of the carbonyl group. Then the pi bond to the oxygen atom breaks up, and then the oxygen atom then have the ability to form sigma bonds to another species, usually a hydrogen ion. So rather than displacing another group, which usually happens in nucleophilic attack, you have the attacking nucleophile, which where we use Z the other time, to the carbonyl of the aldehyde or ketone. So that's why this reaction is referred to as nucleophilic addition reactions. Now we want to consider this, let me say, we have this 9, though I listed 10 here, this 9 reactions that shows or demonstrates the nucleophilic addition reactions which we see vividly in aldehydes and ketones. Some of these reactions, well, most of them, you have come across in your 191 practical class, and which I want you to look at the chemistry very well and refer back to your 191 practical class. I have 1 to 9 there, which we're going to treat. Reactions with toluenes reagents, reaction with derivatives of ammonia, more or less a condensation reaction, because small molecule of water is being left off in this particular system. The information of your cyanohydrins when it reacts, the carbonyl reacts with cyanides. Then there's very important number 4, where you have your Grignard reagents reacting with your carbonyls to give very important compounds. Then your carbonyl reacting with alcohol to produce your acetals. These reactions too are used as protective groups in organic synthesis. Then we have the reduction reactions using simple reducing agents like lithium aluminum hydride. There are quite a number of them like that. Sodium borohydride and some others. Then number 4, also a reducing reaction with Fehlin solution, which you have in your 191, where you observe decolorization and other things like that. Then your hydroform test, unique for methyl ketones, where you have yellow precipitates being formed, and you dry it and you take the melting point of these crystals. They are unique, it's characteristic. You can easily say, oh, this is the type of ketone that has resulted in producing our iodoform. Then the last aspect is the Clemenson's reduction, which I think I saw another analog reaction I compared it with. They are quite simple. Let's quickly go through each of them. You will recall that whenever you oxidize aldehyde, you will get your carboxylic acid. We have done that earlier, but for the reaction of toluenes reagents with carbonyls, we normally refer to this reaction as giving silver mirror, and it's specifically for detecting our aldehyde. We refer to it in the lab, your 191 practical class, as toluenes test. Now, when the aldehyde is mixed with toluenes reagents in the test tube, you have solid silver being formed. Now, on the wall of the test tube, you have the silver being deposited, and you can see the glittering, the mirror effect. And that is where what confirms it's an aldehyde, and at the same time too, we refer to is that is what is responsible for it being called the silver mirror test, specifically for aldehydes. And you can see it's an oxidation trend. And that's why I have that earlier slide, because you are going from aldehyde, you are moving to a carboxylic acid derivative. So that's oxidation trend, utilizing your diamine silver 1 material, which is actually a complex, where my cursor is over here. Now, I said don't bother about this because of time. If you like, you can read it, it's good. Now, the condensation aspects, that is when you add derivatives of ammonia. Ammonia itself is NH3. And when one of the hydrogen is replaced by a Y group, I'm going to give you a range of what Y could be. The lone pair of electron on the nitrogen of our ammonia and its derivatives easily adds up. You can see, consider this and the final product. What is happening here is that derivative of ammonia, there is an H2 here, H2 with O, that is what is responsible for the elimination of water, H2O. And then you now have this carbon of the carbonyl double bonding to the nitrogen. You have your final products in this form. So product form is not very stable with ammonia, but other derivatives of ammonia are capable of forming very important products with the carbonyl. So the reaction is also referred to as condensation because of the water molecule that is being released here. Now I'll give you some examples of what our derivatives could be, that is different Y's here. When the Y is an OH, we refer to that reagent, the ammonia derivative, as an hydroxylamine. After this reaction with our ketone, with the appropriate carbonyl, you now have, we have said, yes, the appropriate carbonyl could be aldehyde or ketone. You now have the final product being an oxide. It's quite common in textbooks, you can refer to this. When the Y is another NH2, that reagent is referred to as hydrazine, and the final product is an hydrazone. I want you to write structures, definite structures to show this. And if on the hydrazine, one of the hydrogen is replaced by a phenyl group, an aromatic C6H5, then it is referred to as a phenyl hydrazine. And the final product after reacting with a carbonyl is phenyl hydrazone. If the hydrazine has one of the hydrogens being an amide, CONH2, then you refer to that ammonia derivative as a semi-carbazide, and the final product is a semi-carbazone. These are examples of what we've been talking about. Over here, you have this aldehyde, an aromatic 1-benzaldehyde, on reacting with our phenyl hydrazine, you have it producing that hydrazone, the phenyl hydrazone over there. This is it over here. I'm just putting it, slanting it. It's still the same thing. So that's your benzaldehyde phenyl hydrazone being produced finally. So please, this slide is what you do in your practical CHE 191. This product, like I said, they are quite useful for identifying your carbonyl compound. And you will recall in your 191 practical that you've handled 2,4-dinitrophenylhydrazine, which happens to be orange in coloration. On reacting with your carbonyl, it yields a yellow solid. And that yellow solid is the 2,4-dinitrophenylhydrazone that, if you take its melting point, it's even characteristic of, you can easily say, no, this is the type of carbonyl compound that I have over here. So this is a little class work But because of time, we won't go into details of it. But I want you to pick, I have several examples of carbonyls here. This one is an aldehyde. This is also an aromatic aldehyde. Take each of these 5 and react it with, take it and react it, that is, take it as this moiety, react it with each of these ammonia derivatives and be able to give equation of the product that is formed. So write out the condensation derivatives formed from each of that. I wish you can name this ones. Yeah, it's quite straightforward. Like this one now is a 2-methylpropanol, and so on and so forth. I've given you the next one as benzaldehyde. Now, another reaction is the addition of cyanide to form our cyanohydrine. I'll give you a vivid example for that very soon. When you add your cyanide to carbonyls, you always obtain your cyanohydrine. This method is very important for making mixed acid and alcohols. The alpha carbon to the nitrile group is with alcoholic OH in the cyanohydrine, and the CN of the cyanohydrine can be further hydrolyzed to give the corresponding carboxylic acid. And you will always notice that the final product produces or possesses an extra carbon to it from the carbon of the cyanide that is coming up, this one. So this is your carbonyl. So there is the extra carbon coming up there, and that final product there is the cyanohydrine. These are, you can, instead of AG, you can replace them with specific, more specific. This is an example. If you have propanone with this cyanide, you produce your cyanohydrine, and that's where it is. But we said it's an interesting reaction where further hydrolysis yields notable products over here. Now, like that product, the 2-hydroxypropanoic acid happens to be lactic acid, which is very important in your yogurts, which we all love taking. The acid is industrially formed naturally by the action of the bacteria Bacillus acidilactic on sugars. And the acid produced is also utilized in dyeing and leather industries. So we have this as another example of a cyclic cyanohydrine, utilizing, starting with benzaldehyde as our aldehyde that is there. Another important one, which I said the other time, is when you react any of these carbonyls with these Grignard reagents. Now, Grignard reagents, how do we even form Grignard reagent? That one we treated under ethers. If you recollect very well that under dry ether, magnesium will react with any alkyl halide to produce our Grignard reagent under a hydrous condition. So over here now for this ethyl bromide, it will result giving us the ethyl magnesium bromide as our Grignard reagent. So this Grignard reagent has the chemistry behind it, why it's so reactive, is that the carbanion is on this side of the metal magnesium, and then we have the other side. So the Grignard reagent, as its way, has the carbanion, which I've shown you here. Hence, the nucleophile is a strong base all the times. Consequently, aldehydes and ketones undergo nucleophilic addition reactions with this Grignard reagent. Let's see some few examples. When the simplest aldehyde, which is methanol, reacts with any Grignard reagent, it finally gives a primary alcohol. Please take note of it. Though I'm giving you a specific example, anytime the simplest methanol reacts with their Grignard reagents, it results to a primary alcohol. In this case, we started with butyl magnesium bromide on the methanol, and we are finally, of course, it first formed the alkoxide, I should have said that. Then finally on hydrolysis, it's kind of two-step reaction. We give that primary alcohol, which is 1-pentanol in there, and you can see an additional carbon on our Grignard reagent over here. Now, any other aldehyde will react with Grignard reagent to produce a secondary alcohol. Take cognizance of that. whether starting, the first one was mesana, whether you say this esana, propana, butana, whatever, they will all react with greener reagent to produce a secondary alcohol in that perspective. So, but for ketones, generally, ketones will react with any greener reagent to produce a tertiary alcohol all the time. So please take note of that, and you can easily predict this. Usually, we represent it like this. That is the first stage of the formation of the alkoxide with the greener reagents, and then the working up, or rather hydrolysis, to give that final product, depending on what is the structure of your starting carbonyl compound. I have these few examples for you to work up with. What will be, like, it's supposed to be a classwork, and that's why I have my answers here. If you have each of these two different greener reagents reacting, that is, you pick I, reacting with hexana, give the equation, reacting with 3-heptanone, give the equation, and that's the third one, they do vis-a-vis with II. Now, what are the products we have in each case? That's it. And here I have the answers for you. I want you to sit down and get yourself, accustomed to working out these reactions. They're not far-fetched. We have the addition reaction with alcohols that give that acetals that are also utilized in protection reactions in organic synthesis. Over here, the acetal is actually a diether. We have treated ethers the other time, carbon, oxygen, carbon, oxygen sandwich between two carbon. So formation, and this reaction is mainly for the aldehydes. They easily add to alcohols once the reagents are dry and under acid as catalyst to produce our diethers. So this is an example of one, starting with SNR, you result having your 1,1 diethoxy-SA. This is an example. The other reactions 6 to 9 are reduction reactions of aldehydes, and I guess we should, let's see one or two of them, but these are straightforward reactions which any hydrogen in any transition metal is an agent of reduction, a reducing agent. Likewise, lithium aluminum hydride, that's why I put ETC. If you go and observe the slide where I placed that 6. So aldehydes and ketone can be reduced back respectively to primary for aldehydes and then secondary alcohol for the ketones. So utilizing any reduction reagents there. So these are quite simple examples of utilizing your reducing agent. Once they are there, this is an aldehyde giving the primary alcohol. This is a ketone giving the secondary alcohol in that example. This one too you have in your chemistry 191 practical, where you utilized your Fehlin solution, and aldehydes are capable of reducing our copper 2 to copper 1. That is what is happening. Your alkaline solution of your copper 2 tartrate is referred to, is what is referred to as our Fehlin solution 1 and 2. So it's a clear royal blue solution, but after warming with our aldehyde, it gives orange yellow precipitate of copper 1 oxide, and that is indicating that there is an aldehyde there. Likewise too, you have the iodoform test. The iodoform test is specifically for methyl ketones, and over there, that's it here. Like propanone now, you have it undergoing iodoform test to produce that yellow precipitate of CHI3, which is our triiodomethane, a solid that characterizes that it is a ketone is present. The last one is the Clemenson's reduction, and that is where we're stopping right away. And you have assignment. In Clemenson's reduction, you have zinc amalgam in acid, converting carbonyls to a methylene moiety. So another sister reaction is the Wolff-Kishner. The reagent here is utilizing our hydrazine under basic condition, whereas this is under acid condition. But the two of them give methylene, converts the carbonyl of the ketone to methylene, and that is how you have it over there. So these are vivid examples, or rather some things you can practice with to have that. It's 10 o'clock already, and I guess you had a nice time in class today. There's some, yes, thank you very much for supplying all the information here. I'm grateful for that. You've been wonderful. Nice having you for this class. I wish you well. So Tuesday next week, we are commencing our 176 lectures again. Thank you for being there. You've been so great. So do I say, thank you.